We'll show them. I'll record it so that they'll know exactly what they're missing out on. All right. So what happens to the voltage across R1 when the switch is closed? That means that this switch S looks like that. It's closed. You want to think about what happens to the voltage across this branch. And whatever that voltage does, R1 will do the opposite of it. All right, just a few more seconds. At 112. Sort of split. So what happens to the equivalent resistance of this branch when I add this resistor R2? Does it increase or decrease? It decreases. So the equivalent resistance decreases of this branch. That means that the voltage is also going to decrease, right? So that means that this voltage will increase. So A is the right answer. What happens to the voltage across R4 when you close the switch? I already said this, sort of. Stop at 22. Very good. B is the right answer. Have I told you the church riddle? My boy told me this. Did I tell you all this one? All right. What is in the church but not in the steeple? It's in the minister but not in the people. You know, like the thing on the top of a church. The big pointy thing on top. No, it's a riddle. What's in the church but not in the steeple, in the minister but not in the people. You give up? The letter R. Oh. Oh boy, tell me that one. Y'all just missed out. It was rollicking good time. Alright.
Now it's going to be all smooth sailing. Y'all.
Right.
All the fun.
All the fun, John. Yeah, so just like we said before, if I add a resistor in parallel, it decreases the equivalent resistance, so that decreases the voltage across that as well. Which resistor has the greatest current going through it? If you assume all of these are equal. We had a similar question before on a quick test. Which has the greatest current going through it? You want to think about how your current splits up as it goes through here. So if my current comes here, it's going to split in a particular way, and then it's going to come back together over here, and then over here, it's going to split in particular ways. So think about how that current splits for these different pairs of resistors. R1 and R2, R3, 4, and R5. current's going to be greatest where the resistance is what? Smallest, yes. All right, just a few more seconds. 1:45, I'll stop. Okay. D is the right answer here. Because it's not just smallest, but smallest relative to the other path. All right, so here, you'll get the same current actually going through R1 and R2, and then it'll come back together. And here, you'll get a bigger current through R5, because R3 and R4 together have twice the resistance of R5, and so more of the current is going to go through R5. So while you got the same currents over here, I and I are equal, you're going to have a much bigger current over here through R5 by factor 2. What is the current in branch P? Stop at 1 minute. 5 more seconds. All right, D is right. Notice while the direction for the current in P is given, you don't need to know the direction because you know that that current has to be going in this direction. Because if I have 8 amps coming in here and 2 amps here, there can't be some incoming current. It has to be outgoing current, and it has to be 6 amps because 8 equals 6 plus 2. Did I mark that correct? Yeah. Follow? What rule is that? That's the junction rule, right? Yeah, Andrew?
What about the 8 amps?
What about the 8 amps?
Well, I thought like 5 plus 8.
Well, what is this current right here?
That's 3.
Right, so there's 3 amps here. So 3 and 5 come together and give you 8, and then the 8 splits into 6 and 2. So notice these numbers just represent the current in these particular wires.
Okay.
All right? Ammeter is connected between points A and B, which the 4 resistors are identical. And what's the current through the ammeter? 4 identical resistors, what's the current through the ammeter? Y'all should have had this in lab too, actually. What is this called? Y'all know? This is a Wheatstone bridge.
Makes horrible bread. Wheatstone.
Right. It's used to measure unknown resistances. Don't really use Wheatstone bridges anymore, but people used to use them. If I have all 4 resistors here are identical, what is the current there through that branch, through the ammeter? What is the current? All right, I'll stop at 110. 110. Just a few more seconds. E is right. In case you're not in lab, let me show you. So I have a certain current coming up here. It comes here and that current splits. It splits evenly, right? So because I have all 4 of these resistors are identical, And by the way, if you're confused by the way that this is written, this is the same circuit as what I have here. Those two are the same circuits. You're just drawing them, I don't know why they draw it like that, but they do draw it like that. They being like, I don't know, engineers or whatever. Huh? Fancy people, yes, engineering type people. Anyway, those are the same circuits. As my current comes along here, I see a certain potential drop, minus IR, and I see that same potential drop over here, minus IR. So when I get to these points, my charges have the same amount of energy, because all they've seen are an increase in energy due to the battery and a change in potential here that are equivalent. So at points A and B, my charges have the same energy. That is to say that the difference in potential between points A and B is equal to 0. Because if they had the same energy at A and at B, the difference in the energy per unit charge is going to equal 0. So VAB is equal to 0. And if V is equal to 0, since V equals IR, I is also equal to 0. V equals 0, so I equals 0. All right? That's called a Wheatstone bridge, but you don't need to know that for this class. Which of the equations here is valid? I think this is our last question. So which one of these is correct? And here the numbers are sort of jumbled up, so you have to be a little more careful in looking, checking them out. $15 more seconds. Stop at 1:30. Very good. C is the right answer. Just want to start with the first part. So here I have 2 is the first part. So for part A, I'm going in this direction. Going in this direction with positive 2. And then I get minus I1. That's correct so far. Minus 2I2. That would be correct right here. But then I have this minus 4I3. So, or excuse me, that was at B. So B is not correct. Similarly, A is not correct. Y'all follow that? Okay. We'll come back to C. Is it correct? D, I3 minus 4. That would be 1I3. So that would be going in this direction because it's positive. I'm going against the current. So one can hear it, D. I3 minus 4. Well, that should be positive 4 because I'm going from low to high. And it should be plus 2I2. It's all jumbled up here. So D is not right. E is 2 minus I1. Starting here, going in this direction. 2 minus I1, so far so good. Minus 3I3. That should be plus 3I3. And it should be minus 6. And then there should be an extra term for this 1 ohm resistor, plus 1I3. So that's not right. So C is the right answer. Let's just trace it through. 2 minus I1, that's starting here. Minus I1 because I'm going with the current. minus 4 because I'm going from big to little side, from the positive to the negative, from the high potential to the low potential. Minus 2I2 because I'm going with the current, and then I come back, and that's all equal to 0. So C is the right answer.
Actually, you can figure it even faster. Count the amount of things, because all the other ones have 4. That's the only circuit that actually has 4. All the other possible circuits in that circuit has 5.
You're right, yeah. You could do that because you have that extra resistor in the right loop. All right. We've done this, so you'll see a multiple choice question like this. I think y'all are okay on it. All right. Couple more things in this chapter. We will wrap it up today. On Wednesday, we're going to move on to chapter 5, and then we'll continue on with chapter 5 on Friday. But on Friday, I'll also if you have questions, we'll open up class with questions about the exam on Monday. So if we spend all that time on Friday for chapter 4, reviewing chapter 4, then we will not move on in chapter 5. Is that clear what I mean? Mm-hmm. Okay. I will post these concept tests. Make myself a note. Go give me just a minute, okay? So don't forget to do this. Chapter 4 is almost over. We just have to do home circuits, and then 20 pages.
Let me find the homework. Okay, now it's 68, so 13.
Y'all should be done with the homework, more or less, right? Y'all should be working through the homework. That's good practice for the exam.
Of course.
We started with RC circuits last time.
We wait until we learn everything so we don't come here asking stupid questions that we haven't gone over.
Right. That is a not so good student. And I used to be a not good student, but now I'm in this class and man, I'm on top of things. I'm a good student. But I used to be a bad student when I was an undergrad. But now, I know some of you are good students. And right. You can still do well as a bad student, but it's just a lot harder because staying up all night is not good. You want to do the difficult things first and then do the easy things. I've learned that as a student.
It's hard to clean up a train wreck in my mind.
It's hard to clean up a train wreck, right?
And by train wreck, meaning being confused about things I have no idea about.
Right. Mm-hmm. All right, guys. So we talked about capacitors and how they charge and discharge last time. Remember, when you're charging a capacitor, it charges as this exponential function, and so the charge gradually accumulates on the capacitor. As I turn it on, there's going to be current that flows through this resistor that is going to cause charges to accumulate on the capacitor, and that current has a certain flow rate. We'll see that in a second. And then once this capacitor is fully charged, all the current stops. Right, so we can characterize the charge in this way, that as I'm charging the capacitor, it gradually approaches this Q value, this maximum Q. That maximum Q is equal to the capacitance times the voltage, as we saw in the previous chapter. And then this is the exponential function. I don't think this is on your equation sheet, but I'm going to put it on here.
It is.
I'm going to put all these exponential functions on your equation sheet. So just make sure, you'll probably have a simple question, just ask, what is the charge, or what is the current, or what is the voltage at a particular time. Make sure you know how to use your exponential key on your calculator. You probably don't use it very often. So just make sure that you're able to do that. There's some homework questions for you to practice. Likewise, our exponential function here is our current is decreasing, because as we get more and more charge on our capacitor, we get less and less current. So our current looks like this. It gradually approaches 0. And that's the exponential function. It starts out at its maximum value, which is V over R, and then it goes down from there. Let's see, there's the exponential functions. I've already drawn them, but that's current versus time and charge versus time. Now, after you charge a capacitor, you can remove the battery, and the charge stored by the capacitor can be used at a later time, like the boost pack. You remember the boost pack? That's what he was doing. He charged at the capacitor with his alternator, and then he used it later on to crank his car. So you have a capacitor, it discharges through a resistor, and they all decrease with time as an exponential function. So our charge, our current, and our voltage all have the same function. They look like this. Our charge is equal to Q times e to the minus t over RC. Our current is equal to V over R. That's our maximum current times e to the minus t over RC. And our voltage is just going to be the voltage, our maximum voltage times e to the minus t over RC. There's a function on the next page. I'm going to draw it here, but this function all looks the same. It all looks like this. It's an exponential function, and it all starts at some maximum value. Whether it be your maximum charge, which is Q equals CV, your maximum current, which is V of the battery over the resistance of the, or V of the voltage that's on your capacitor, divided by the resistance, and then our V naught, which is our voltage on the capacitor. Yeah.
Somebody brought a road for Q, big Q times 1 minus E to the.
Right. That is charging a capacitor. This is discharging a capacitor. So charging a capacitor, that's correct. Your Q increases, but for discharging a capacitor, Q decreases. All right, and so that function, this is a decrease exponential function, and the 1 minus e to the minus t over RC, that's an increase in exponential function. All right? I'll put these on your equation sheet, so, but you do need to know these forms, like how they look. Like I might just ask you to sketch out what charging a capacitor looks like, or what discharging a capacitor looks like. That's part of a question. All right? But y'all could do that, I think. It sort of makes sense if you think about it. Right? Why they act in this way. If you just know that it's an exponential function, that's sort of the hard part. All right. We use the time constant to describe these circuits. There's that. That's that function that I drew. And the time constant is called tau. And the time constant is just equal to, in our circuit where we have a resistor and a capacitor like this with R and C, our time constant is just a product of those. So our tau is RC. The units for the time constant are seconds. That was a switch, yes. And we say that after 10 times the time constant, the capacitor is basically fully charged or discharged. So remember, if we're charging a capacitor, this is charging, placing charges on that capacitor, our Q versus T, this would be little q, Q versus T looks like this. It approaches big Q, which is our maximum charge. We say that after 10 tau, which is roughly here, after 10 times the time constant, we say that it's fully charged. This is never actually fully charged, right? An exponential never actually gets to that point of Q, but we say that for all practical purposes, after 10 tau, the capacitor is fully charged. We say it. They say it. I just say it because that's what they say. But that's true, that when your exponential function gets to 10 tau, it's fully charged. Rob?
It's not. It's discharging at a constant rate.
I don't know, Rob. Like physically, why don't the charges come off at a linear rate?
If you're not getting anything, it doesn't come off at a constant rate.
Mm-hmm. Yeah.
Yes, just net abundance, so it just comes off out.
Yeah, I think that's it, Lauren, that when you have a bunch of charges, it's like they're shooting them off really quickly because you have a bunch of positive charges there all together, and so they're going to repel charges very quickly, but then as you get fewer and fewer charges, yeah.
It's like if you fill a gallon of water. Like if you have a gallon of water and you punch a little hole, it'll come out fast first because there's a lot of pressure, a lot of extra forces, and then once you lose pressure,
Right.
it'll come first.
Yeah, that's a similar thing. Your energy decreases with time. Thank you, Mark. All right, let's try this little quick test. These are pretty simple, but let's try it out. Y'all do that. I'm gonna run and no, I'll bring it next time. I might bring it to this. If you haven't gotten the answer yet, you're probably thinking a little bit too hard about this. We want to know the time to fully discharge the capacitor. Stop about 2 minutes, about 12 more seconds. 5 seconds. 2 seconds. Alright, let's see. B must be put. B is not right. What is B though? How'd y'all get B? That's the time constant, right? But remember, to fully charge or discharge, it's not the time constant, it's 10 times the time constant. So A is actually the right answer here. B is a good wrong answer because you were thinking on the right frame. But I know that tau is equal to R times C. That's going to be 1 mega ohm times 4 microfarads. A mega is 10 to the 6, micro is 10 to the minus 6, so they just cancel out. And so I'm just left with 4 seconds. But then 10 times tau is equal to 40 seconds. So A is the right answer. All right. Let's do a quick example. So let's say I have this circuit, and after 20 seconds, I want to know what is the current in the 2 ohm resistor. So I want to know what is this current right here. Now, in order to do this, we want to consider this time after 20 seconds, because the current to this branch is going to change, right? Based on that, the current to this branch is going to be I equals V over R times e to the minus t over RC. Right, that current is going to get gradually smaller and smaller. And so I want to know, how does that change? And so I want to find out what is the time constant for this part of the circuit. And so my time constant is going to be 1 farad times 1 ohm, which is 1 second. And so after 20 seconds, that capacitor is fully charged. So the current then in this part of the circuit at t equal 20 seconds is equal to what? What's the current in that circuit? Remember, current versus time, I versus t. As we're charging, looks like this. All right, so after 20 seconds, that's going to be 10 tau, which will be out here roughly. what is our current going to be? It's going to be 0. So I at t equal 20 seconds is going to equal 0 amps. That is, that part of the circuit is no longer going to have any current. You're going to have all your charges deposited on that capacitor, and so no more current will flow to that part of the circuit. And so, for all practical purposes, we can just say that part doesn't exist in order to find the current across the 2 ohm resistor. So this becomes a circuit that's quite a bit simpler. It's just a 2 ohm and a 1 ohm resistor with 6 volts. And so the current across this 2 ohm resistor is going to be the same as the current across this 3 ohm resistor, which is the equivalent, which is 2 amps. Yeah, was it?
Can you go back up?
Mm-hmm.
So, wouldn't that be 10 seconds?
Right. I mean, 10 times the time constant would be 10 seconds.
So it would be 10 seconds.
So anytime past 10 seconds, yes, your current would be 0.
Okay. Just making sure, because you put 1 second now and you multiply by 10 before and I'm like,
Right, yeah. So at 10 tau, at 10 seconds, the capacitor is fully charged. And the current has gone to 0. Go with me on this so far? All right.
What if in less than this?
It's a little more complicated. You'd have to figure out what is the actual current there. Let's see. If it was less than 10 seconds, this is what it would look like. And I wouldn't give you a problem like this on the test, but just I'll sort of step you through it. Is that clear? I'm not going to ask you something like this. Well, let me show you. You would say, I'm going to redraw this just a little bit. There's my 2 ohm resistor. I'm going to redraw this without the 1 ohm, without the capacitor. You would first have to find out what is the maximum voltage across this resistor, which we could find, right? That's the problem we've done. So you'd find that voltage, and so that would be the maximum voltage here. And then you would have to find what is this then. So you'd say whatever that voltage is divided by R, that's going to be my maximum current to that capacitor. And then if you know the time, you could calculate what this current is. Go with me? So once you find that current, then if I want to know the current through the 2 ohm resistor, or once you find that current, you can also find what is the voltage at that particular time, because you know the current, you know the resistance, so you can find the current, the voltage, and whatever that voltage is going to be the same voltage that we have on that 2 ohm resistor, because those two are parallel. So there are a few more hoops you have to jump through. You could probably do them, but I'm not going to require you to do that. All right. So let's consider this circuit. At 5 seconds after closing the switch, what is the charge on the capacitor? Let me look and see.
there's 2 switches.
There are
I'm
2
guessing
switches,
it's the one that
right?
would actually complete the circuit and actually start charging anything.
Well, let's just leave off the top portion of this, okay? So we're going to leave off this portion altogether. It feels like it doesn't exist. And let's just close this switch. Do I have another? No, I don't have another. I think I used to have another question that followed.
Yeah, there is. It says after 20 seconds, the capacitor is going to be charged. You
Oh, yeah, okay.
Switch.
All right, yes, so let's leave this then. Sorry if you scratched it out already. You should get one of these erasers. They're kind of cool. So if I close the bottom switch, what is the charge on the capacitor? All right, so I'm just considering now this circuit because the top switch is open, and so it doesn't really exist. I can figure out what is my time constant first, because I want to know if it's fully charged, then it's really easy, right? It's just I need to know the maximum voltage. So my time constant is going to be what? 2 seconds. That's the resistance, which is 2 ohms, Remember, I'm considering this circuit. A 2 ohm resistor, a 1 farad capacitor, and a 6 volt battery. By the way, a 1 farad capacitor is a really big capacitor. You don't usually encounter capacitors that big, but I'm just using these round numbers to give us easy answers. All right, so tau is 2 seconds, and I want to know the charge after 5 seconds. So I can't say that it's fully charged because it's not fully charged. Only after 20 seconds would it be fully charged. So what is the charge on the capacitor? Well, I would say that Q is equal to Q naught, or my maximum charge times 1 minus e to the minus t over RC. Remember, this is that function that looks like this. If I plot Q versus t, it looks like this. That charge is gradually asymptoting to or gradually approaching a maximum value of Q naught. All right, this is going to equal CV. C is 1 farad. My voltage is 6 volts. Times 1 minus e to the minus 5 over 2. I have the wrong answer in my notes. Can y'all tell me what this number is? That's 6 times something. What's e to the minus 5 over 2? That is e to the minus 2.5. What's e to the minus 2.5?
Oh, E being the actual weird
Right, the
natural log,
natural log, right.
not some strange constant.
Right. Somebody tell me what e.
67 something.
That's e to the minus 2.5.
Oh, no, wait, hold on.
0.082.
Never mind, I forgot to do the negative.
What is it?
0.0820.
0.08. We'll just call it 0.082. Make sure you can do this. So you probably don't use your exponential that often. 0.0821.
That's what I got.
5.507, or you could just call it 5.5 coulombs. All right. Everybody got that okay? Are you feel comfortable doing that type of calculation? You don't have to do it, but you'll have the equations. I mean, you just have to sort of know what to apply them and how to apply them. All right. So after 20 seconds, the capacitor is fully charged. 20 seconds is 10 times this time constant. You open the bottom switch and you close the top switch. So this might be a circuit that you would have to charge a capacitor and then discharge a capacitor. So for example, if this was like your flasher lights in your car, this would be the actual light. And so it would charge and discharge on a particular time frame. It would take 20 seconds to charge, and then it would take a certain amount of time to discharge. So now in this second part, this provides a source of current when the battery is not
What is it, available?
available, yes. Sorry, I don't know what happened there.
It's not Ava.
It's not Ava.
Change its name and move to a different country.
So I thought I had a different question. Let's do a different question actually. So let's say part B of this question. Let's say that you close the bottom switch, or excuse me, open the bottom switch. And close the top switch. What is the charge after, no, let's say what is the current, rather? After t equal 10 seconds. All right, you want to do a similar thing. Here I have a circuit that looks like this. I just have my 1 farad capacitor with a 5 ohm equivalent resistance. That's taking into account this resistor and this resistor. And so my time constant is 5 seconds, so I'm only at 2 times the time constant. Remember, your current is going to be waning. So I is going to be equal to my maximum current times e to the minus t over RC. I draw that yeah, so this, remember, is that function that looks like this. I versus t looks like that. My current is actually decreasing with time at a particular rate. And so I want to figure out now what is I naught. Okay, in order to do that, we need to figure out what was the potential across this side right here. Or we could just say, do we know the charge on the 1 farad capacitor? Is that something we've calculated? Yeah, we know that there are 5.5 coulombs here. And if there's 5.5 coulombs there, I know that the voltage has to be what? I know that Q equals CV. So if C is 1 and Q is 5.5, then my voltage also has to be 5.5 volts. You with me? Kind of. Look, after I get rid of that bottom part of the circuit, I have a certain amount of charge that is on this 1 farad capacitor. And as a result, that capacitor now is a source of voltage. And so I know that I have 5.5 coulombs on that capacitor from the previous part of the problem. So I know then that V is Q over C. So I know that I have 5.5 volts now across that capacitor. So it now provides a voltage source of 5.5 volts in this new circuit.
What's Q, what's C? I know C is 5.5.
Oh, C is equal to 1. Q is equal to 5.5 coulombs. We got Q in the previous part of the problem. When we were charging that capacitor, a certain amount of charge was at 5 seconds, right. But then at 5 seconds, yeah, at 5 seconds. So that's assuming that after 5 seconds, we open up that switch and close the top switch. Huh? But now we're waiting another 10 seconds.
Another 5 seconds after.
Right. No, we're waiting a full 10 seconds. I'm sorry. Is this confusing you all?
Yeah.
All right, let me go back and explain. So look, our first step was that we closed this switch for 5 seconds. We put 5.5 coulombs of charge on that capacitor in that time. Then we open this switch again, the bottom switch, so the battery goes away. And then we close the top switch for 10 seconds. What's it?
Wouldn't this be affected by the fact that you have different resistance in both sides? No?
Now you have two independent circuits that are working. So the first circuit, you just have the bottom part, and you have to tell how much charge goes on the capacitor. And then the bottom part goes away, and now we're just looking at the top part. And the top part, we say, okay, now we got 5.5 coulombs of charge on this 1 farad capacitor, or 5.5 volts, and I want to know what is the current that's being produced by this. Y'all look very, very mad. Are you mad?
No.
Yes. Okay. So, now it, what, Catherine? Stressed. Okay. Okay, so now in the top part of the circuit, I have 5.5 volts off of my, I have 5.5 coulombs on that capacitor. I close that circuit on the top so that it opens up, allowing that capacitor to discharge. The bottom is now open, so it's not in there. And now I just want to know what is the current after an additional 10 seconds. So 15 seconds has now elapsed. 5 seconds to charge, and now 10 seconds to discharge. Give y'all a second. Okay. So here, my I naught is going to be V over R times e to the minus t over RC. And that's going to be I as a function of t. It's 5.5 volts over my resistance, which is 5 ohms, e to the minus t, which is 10 seconds, excuse me, over the RC, which is 5 times 1, 5 ohms times 1 farad. So it's e to the minus 2.
So that's 0.149.
What'd you get?
0.149.
Okay, R is caught 0.15. That's what I got too. That gives us I at 5 seconds. Or 10 seconds, rather. I naught is this current. Because I have 5 volts potential on that capacitor. I have a 5 ohm resistor. So that's just Ohm's law, V over R. 5.5 over 5 is I naught. And that is, 1 point something. That's 1.1, right? Yeah.
If you ever give us a time constants first, when I had a problem, will we assume that we need to multiply by 10 to work out the problem?
Well, in this case, you didn't need to multiply by 10.
I mean, in future reference, if you give us that rear T.
Okay, yeah, if you have tau, the question is the capacitor fully charged or is it fully discharged? So if it's fully charged, that is the amount of time that has elapsed is more than 10 times the time constant. In this case, that would be, for the top part, it would be 50 seconds. Has 50 seconds elapsed because our time constant is 5 seconds. So 10 times 5 is 50. Remember, this is our time constant, this R times C. Then it's fully charged. And if that's the case, then what's our current? Or it's fully discharged. What's the current after 50 seconds? In this circuit, the top circuit. You have no idea? It's what, Mary? Well, you don't need to plug it in though, because the current after it's fully discharged is what? Is 0, right? So after 10 times the time constant, there is no current. There's also no charge on the capacitor anymore. It's completely discharged. So if it's fully charged or discharged, the problem becomes pretty trivial, like we had a problem before. If it's not fully charged or discharged, then you have to consider this exponential term. Okay?
If you get what I'm doing, when we see the next one.
Okay, let's see what we got, and then we'll wrap up.
That's where I was talking. Like, you say 1 second, but should we treat it as 10?
No, the time constant is 1 second here. That's tau. It's equal to 1 second.
So we don't need to treat it as equal to 10.
No. The only thing is, this capacitor requires 10 seconds to fully charge and 10 seconds to fully discharge, given this circuit with this resistor. All right. So here, what is the capacitance C? 1 is the time constant. I have 10 mega ohms as the resistance. What is C? Watch your units too. Notice the units here are mixed up. Yeah.
Charging and discharging at the same time.
Yes. They require the same time to discharge and charge.
That's like working a cell phone then, because it takes like maybe 2 hours to charge.
Those aren't capacitors. Those are batteries. And so capacitors, it's like the difference between an auto battery and that boost pack, right? Capacitors don't work. They don't convert chemical energy to electrical energy. They actually have actual charges that are inside, and those charges are allowed to leave over a certain amount of time. So that's a different process. All right, about 10 more seconds. I'll stop at 150, I guess. 150. Well, guys, I'm going to take D out, okay? Because it has the wrong unit. I think I probably took it out on the test. So D is not the right answer. Huh?
I thought it was a trick too.
What, putting in the wrong...
You're putting in the wrong
Yeah.
units and confusing it.
It might have been a trick. I used to be trickier than I am now. But I know y'all think I'm kind of tricky, don't you? All right, 225, I'll stop. I think that's everybody. All ready to go anyway, aren't you? All right, C is the right answer. It's supposed to be easy, guys. So tau is equal to RC. That's 1 second equals 10 mega ohms times C. And so if you work this out, C is 0.1 microfarads. 10 mega ohms times 0.1 microfarads. Those cancel, mega and micro cancel out. 10 times 0.1 is equal to 1, which is our time constant. All right, y'all have a good day. So we'll do household circuits next time. We'll finish this chapter next time for sure.